Afternoon. What we'll do is after each talk we'll give about 5 minutes. We're planning to have about 5 minutes for Q&A as we get moving along. So we won't do it at the end of the session. We'll do it after each talk because each talk is a little different, and that way you'll be able to ask your questions sort of real time rather than holding on to them. Our first talk this afternoon is going to be by Brendan Brown, and he's going to talk about applications for drones on remediation projects. So kind of a real cool kind of shift in technology applications to our projects to take a look at. So with that, Brandon?
Thank you. So I'm excited to be here today. My colleagues and I have executed hundreds of drone flights collecting data from environmental sites, and I'm always still amazed and excited about some of the data sets that they can collect and how we can work with them. So first, I want you to imagine yourself as an early explorer of the cosmos, but you're using rudimentary tools to figure out what's going on. So you can look at the whole sky, but it's kind of blurry, or you can focus in on one small area, and then you have to painstakingly go from area to look at different things. Now I want you to pretend like you've been instantly transported to the future, and now you have the most powerful telescope ever created at your disposal. You can see the cosmos with perfect clarity. You can look at supernovas, you can detect elements, you can look at planets in other galaxies with perfect clarity. But it's almost too much data all at once. You don't quite know where to begin with all of this massive data set that you've never had at your fingertips. So that's sort of where we are with some of the drones and sensors that we have now to assess sites. But they collect a large volume of data such that it can be a little overwhelming to sort of sort through and figure out what's going on at your site. So today I'm going to talk about some of the drones that we're using and various environmental sensors applicable to remediation projects. We're going to talk how we actually collect this data with the drones and how we process these data sets that we get. And then I'm going to go through a few case studies where we're applying machine learning and other things to query the data and figure out what's going on at a site. So at the base, drones provide really high quality but also high volume data, and they do it in a safe manner. And so this is really important, obviously, in remediation projects where there might be heavy equipment going on or excavations, and collecting traditional field data during a remediation might be dangerous to people. Or the contaminants of concern might be radiological or have other human health concerns, and we don't want people spending that much time in there. So drones can help us out and collect a lot of data safely without having that human exposure pathway. And so there's a lot of different drones that can be used, and the batteries keep on getting better, and then the drones are able to carry heavier sensors, and so you can even put a LiDAR unit on a drone now. And there's numerous environmentally applicable sensors. So LiDAR obviously gives you good topographic data. Thermal sensors can look for thermal anomalies, so they're useful for assessing landfill gas leaks or looking at hydrology, groundwater seeps, or surface water mixing zones. Multispectral sensors can provide information on land cover and vegetative cover, and then there's a lot that you can do with a digital camera besides just take pictures or video of a site. So I'm really going to focus on these three sensors during this presentation. So with a basic drone and digital camera setup, you can do a lot of different things. Most cameras are probably about the same as your iPhone that you have, maybe 20 megapixels. But from when you're flying the drone, typically around 400 feet over your project area, you're going to get, each pixel is going to be less than an inch per pixel. So a very high resolution data set. So you can collect megabytes of data on at your site. So a multispectral sensor gives us information both on the visible and some of that infrared part of the electromagnetic spectrum that can tell us different things. So a little bit more data, probably gigabytes of data per site. And then this is important because each landform has its own sort of spectral signature. So soil looks very different and reflects things very differently than plant matter, and even water and different types of water. And so within that as well, within those spectral profiles, you could have a difference in clay versus sandy soils, or different vegetative species have a different signature as well. And then a hyperspectral sensor provides even more information, both in the visible and in the near and shortwave infrared. And this is important because it can provide us information on mineralogy of a site. So hyperspectral sensors collect almost a near continuous evaluation of that electromagnetic spectrum. And so we can use those differences in those reflectance to look at different minerals and identify them by that spectral signature. And then these are very powerful, and they collect almost terabytes of data per site. So then thermal sensors are really good for detecting those thermal differences or anomalies, good for evaluating hydrology or gas leaks. So now we're going to talk about some of the methods that we use to actually collect this data and process it and begin to analyze it. So before, I did want to mention a few things. In order to fly a drone for commercial purposes, you do have to be licensed by the FAA. You have to register your drone, and then you have to follow some rules about when you can fly and where you can fly. So it's important to keep that in mind. And since we're here in Florida, I did want to note a couple of the challenges of flying in Florida. So there's a lot of airports in Florida, as we all know, and each airport has its own sort of zone of restriction where they control that airspace. And so it's not to say you couldn't do a flight in those areas, but you just have to get special permission from either the airport or the FAA to fly in that area. And then, of course, weather is always a challenge. Rain and drones don't typically mix, although there are a few drones that can handle it. But with our afternoon thunder showers, it can kind of put a damper on a field day. So when we're executing a flight, we want to establish a safe landing zone and takeoff zone. And then we typically fly sort of that lawnmower pattern back and forth over the site. And then if we want our data to be tied to a real-world datum, we need to do ground control, where we lay out our targets and tie those to real-world coordinates. And so one of the basic products that we can get from drones is just from the images themselves via a process called structure for motion. So this is the concept of taking 2D pictures of a 3D object from different angles, and then we use algorithms to stitch those pictures together and deduce the 3D relationships. So how this works at a site is that we're flying the drone over the site, taking pictures at different times, and then using those pictures. Now this is a passive form of remote sensing. It's not like LiDAR where you're sending an active beam, so we're relying on the sun. And so once we take those overlapping pictures of a site, it could be hundreds of pictures, we use software programs that utilize those structure for motion algorithms and put that data set together, and we end up with a 3D model. And so with just a basic drone and a digital camera, we can get elevation projects, a digital elevation model, surface model, we get a nice aerial photograph, and a 3D point cloud, which we can begin to work with and process. So it is similar to LiDAR in that you end up with a point cloud. One of the nice advantages is that you actually get the true color, the aerial photograph as well, and so you can assign each one of those points the color it is in real life. Now, one of the drawbacks is if your site is, say, heavily forested with a dense canopy, since it's a passive form of remote sensing, you're not going to be able to get extremely accurate ground measurements like you would with a LiDAR unit. But in a lot of our remediation sites where there's open, bare earth, these models are highly accurate. So how accurate are they? Well, in general, on a road or an open dirt surface or an open pit, we can generally get within about 1/10 of a foot compared to traditional survey. So a very powerful tool, and actually in terms of processing or the amount of post-processing that goes on, in some ways it can be even better than LiDAR because it doesn't take as much time to process and sort through. And then because these drones and sensors generate so much data, it's really important to leverage Python and some machine learning to sort of unlock these data sets because they're so cumbersome. So now I'm going to go through a few case studies where we're using these technologies for remediation type investigations. So estimating cut and fill volumes, looking at groundwater surface water interactions, and mapping surface features. So with that basic digital camera setup, We can do a baseline survey of a site and then do a survey every week or every other week or every month, and then look to assess the changes in the site over that time. And once we get those 3D data sets in, it becomes quite easy to set up an automated process to calculate volumes to see, well, how much have we filled in this area or how much have we excavated in this area. And so that's what we did here on a project where there was an excavation next to a bridge footer. And then we can also cut cross sections anywhere or make topographic maps. And then what this allows us to do on this particular project, the contractor had to restore the site and grade to a certain elevation to promote the growth of a tidal marsh system afterwards. And so it was really crucial to get the elevations just right. And so what we're able to do is fly the drone and then determine exactly where the contractor needed to do a little bit more grading. So the areas in red were the areas that were graded too high. So rather than having just a few topo spot shots of the elevations that say, all right, well, here you're a foot higher, here you're 6 inches high, now we can provide the contractor spatially explicit GIS-based information that says this area needs to be taken down a half a foot, or this area needs to be taken down 2 feet. So it's important to remember the subject matter when you're executing these projects. We had one project where the client had hired us to remove numerous waste piles at a site. And they had used a drone consultant to estimate the volume of waste piles at the site. And so when our team showed up at the site to remove the waste piles, immediately they recognized that there was way more waste piles than we had been contracted to remove. So we brought this up to the client, and they said, okay, well, let's get an actual professional land survey estimate on the volume of waste piles. And we said, yeah, that sounds like a good idea, but hey, let our drone team do a volume calculation as well, just to see what went wrong. Why did they underestimate the volume so much? So our estimate from our drone team compared pretty favorably to the professional land survey that was conducted to estimate the volume, and the drone consultant was very on the low side. And so what the drone consultant had done is there's a lot of off-the-shelf software processing programs where you put in your data, draw a box, and then it spits out a number. But they weren't really subject matter experts, and they really hadn't done any ground truthing to see what we observed in the field, is that matching up with reality? So it's important to have some sort of sense of what's on the ground, understand your subject matter, but then also have some ground truthing where you can validate your data sets to say, all right, this is matching up with our model. So talking about thermal sensors, so this was a project where it was a tidal river, freshwater, a very long stretch where we were looking to identify sources of surface water into this tidal system. Very vegetated, so miles upon miles that we were investigating, so it could take a really big field effort to evaluate what's going on there. But with a thermal sensor, we're able to detect obviously what the human eye cannot, and so we can quickly identify areas where there's surface water discharge, and then we can go send field personnel to confirm those areas. So a time saver in the field. Similar thermal investigation, this was at a landfill. We were trying to identify PFAS coming off of the landfill, and we thought primarily it was happening in groundwater seeps. So a large area, forested, hard to traverse. We used a thermal camera on a drone while we had the field crews out there as well. And so we were able to quickly identify, because of that heat signature difference, where there was likely groundwater seeps, and then we could sample those areas rather than spending a whole lot of time out there just searching around for groundwater seeps. So this was very effective in identifying those seeps, and they ended up coming back. Most of the seeps did have PFAS contamination. So the next project example is obviously not in Florida. This is a mine site out in Oregon, and a very large site, 200 acres, where we're looking to identify waste piles and map and characterize them. So very difficult terrain to traverse, and so it could take a very long field effort with multiple teams traversing this site to evaluate it. So with a basic drone and a digital camera setup, we can do our ground control points, and we can do some ground truthing where we collect that data, so it's more of a limited field data collection method. Then we can get our data outputs from those, that structure from motion software. And when, we have our high-resolution aerial map, but then we also have a very accurate topo map, especially at this site where there's a lot of bare earth, so it's going to be very accurate. Then when we want to identify potential waste piles, then we can apply a machine learning and artificial intelligence model to that to kind of give us a first cut on where the waste piles are distributed across the site. And this can be really beneficial to cut down on that field effort in investigating it. And then sometimes there might be things that humans might miss out in the field. So on this next project, similar a mine site project, this one was in Utah. There was over 10 million tons of processed ore waste piles in the area that contained both arsenic and iron. And so you can kind of see on the bottom part of the southern part of the site, rather, that reddish color. And that's where the goethite mineral was, which contained a lot of iron and arsenic in it. And due to the prevailing winds, it was pushing those piles and with wind-blown dispersion of those minerals to the north by northeast. And so we were looking to characterize this site. And again, a large site, difficult to traverse, could take a large field effort and a multiple iterative field effort of doing samples, collecting field samples and doing XRF analysis, and then sending those off and then coming back out to redefine this extent. So it could be a really big undertaking. But for this site, we applied a hyperspectral sensor on a drone, which gives us some information about mineralogy. And so for this 200-acre site, we're collecting terabytes of data across that electromagnetic spectrum, and then we can start to separate out, based on the spectral signature, jarosite versus goethite, which were the ore processing minerals that were left over in the waste piles. So with this large data set, then we can apply spectral angle mapping to determine where these minerals are distributed across the landscape. So that's what you see on the bottom right, is our model that we use to develop to predict where these minerals are. And so we can compare this with our field data, traditional field data. So on the right is field data from about 64 samples that were sent off to the lab of arsenic and iron concentrations. And then on the left, we have our model for the mineral goethite, which contains the arsenic and iron. So if we look on the sort of the northern part of the site, we see that our field data is indicating some contamination with iron and arsenic, but not a lot. And then we're seeing a similar result with our spectral angle mapper model as well. And then if we look on the western part, our field data is suggesting that there's really not very high concentrations there at all. And then likewise, we're not predicting any of that mineral over in the western part. So now we have a much higher resolution look at the minerals and the distribution across the site. And it can be a lot more useful, and it can limit our field time collecting all that data and sending off samples to the lab. So we talked about a lot of sensors that are environmentally applicable today to our remediation sites, and how we have a much clearer picture, or we can have a clearer picture of what's going on with our sites as we sort through these data sets. We talked about thermal sensors, multispectral sensors, hyperspectral, and then what we can do with just a basic drone with a camera on it. And the real key to the working with these data sets is leveraging either Python or machine learning analysis to help us sort through these data sets and provide meaningful solutions. And so I want you to think about how you're going to explore your site and what sorts of tools and sensors and methods might be helpful to answer your site questions. Thank you.
Thanks. We have some time for some questions for Brendan. Anybody have any questions? We've got to have some.
So, do you have the availability if someone has a drone program, and they provide you with the data, and you provide these sensors?
Yeah, absolutely. The question was about, if somebody already has a drone and is collecting drone data, can we work with it? Definitely a lot of clients already have drones in their program. And then they collect this data, and then sometimes, since it is a very high volume data, you almost don't know what to do with it. So, definitely we can help out with that.
Question?
So, for example, you have the cal A, cal B, is even the solution, the excavation, drawing. So, what is the base to say which data I can trust?
Yeah, it's a good question about the waste piles and the difference. In some ways, depending on the survey methodology, the structure for motion actually might be a more accurate estimate of an irregular waste pile, just because depending on the survey methods, you might not get every undulation that you do with the structure for motion method, where you're going to have, probably maybe around 40 points per, meter, or 100 points per meter of your point cloud data. So in some ways, some of these technologies are probably more accurate than some of the traditional methods. Does that answer your question?
Yeah.
Okay. Yeah.
So the first top field example, next below, excavate typical mass survey with a drone. So what's the benefit to use the drone?
Yeah, I mean, surveyors are using these technologies. I think sometimes the benefit of conducting it yourself is that a lot of times you're already out at the site monitoring the site, and you already have the staff personnel, you already have geologists or scientists out there overseeing things, maybe taking samples. And so if they also know how to fly the drone, then it's a marginal cost to go ahead and add that data collection at the same time, rather than sending a surveyor out for a completely new mobilization trip. Yes.
You showed some data that I believe were survey data that resolved down to 7/100ths of a foot. And I'm interested in, I don't recall what that exact method was, but would you clarify that for me, and also comment on LiDAR and how that resolution differs, if it does?
So can you repeat the question about the LiDAR? I'm sorry, the second part.
What kind of, your presentation didn't really cover much about, you said at the beginning, not talking about LiDAR, but the technology that you used to resolve to 7/100ths of an inch, what was that method? And then how does it compare to LiDAR resolution? Yeah,
so that comparison was on bare earth surfaces, so a road or bare soil. So if you're going to compare sort of that photogrammetry structure for motion technology to, say, a very dense shrub vegetation, or tall grass, or a canopy of forest, and you wanted to compare ground points, you're really not going to be able to get very good ground points with that photogrammetry, the digital camera-based system. But when you're talking about head-to-head on a hard surface, a road or soil, that's that number that I gave. That was a comparison of about 20 points with the professional land surveyor using static LiDAR, or a GPS-based survey compared to what we got with that model output. And so one of the advantages compared to LiDAR is just the density of points. With LiDAR, depending on the unit, but definitely if it's a plane-based LiDAR data collection, you're going to get a lot more points per square foot with that structure for motion than you will with LiDAR.
Great, thanks.
Any other questions? We got one in the back.
Can you ballpark the cost, typical cost per project or per acre cost?
Yeah, it's got to be the classic cost question and the classic evasion. Let me see how I can do. Can we talk afterwards and give you? All right, thank you.
I was going to put some pressure on him, say, come on, you can do it. Tell us how much it costs.